Is that able to hear me? Those who are online, are you able to hear me?
Yes, sir.
Okay. So we'll proceed with the next part of this chapter. Right. So till where did we discuss yesterday? What was the last topic we discussed? Do any problem based on it? I think we did one problem, right? We'll do another problem and then proceed to the next part. So yesterday when I explained you Faraday's law of electromagnetic induction, I have told you an important point. What is it? That is negative sign. Negative sign is the significance of what? There is something called as Lenz's law, about which I need to show you. But before that, let's get started with a problem. Right? So I hope you're able to see the screen, right? Those who are online, yes?
Yes, sir.
Okay. So let us recollect the concept. What does Faraday's law of electromagnetic induction state? if there is a relative motion existing between the source and the, there is an EMF that is induced. Is that right? So, if I take a circular coil, okay, and what is the value of that EMF, guys? By the way, EMF is equal to minus n into delta phi divided by delta t. And if it is an instantaneous change, you can write it as E is equal to minus n into d phi divided by dt. Is that clear? Now, let us recollect. So, if there is a circular coil of radius 10 centimeter, so if there is a circular coil of radius 10 centimeter, the number of turns is 500, resistance being 2 ohm, is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. Okay, so it's placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. What does that mean? So there is Earth's magnetic field present here, and the plane of the coil is placed perpendicular to the perpendicular only, no? So plane of the coil is placed perpendicular to the Earth's magnetic field, right? Now it is rotated about its vertical diameter through an angle of 180 degrees in how much time? In 0.25 seconds. That is 1/4 of a second, right? Estimate the magnitudes of the EMF and the current induced in the coil. Now first, see, for these kind of problems, right? Whenever they say estimate the induced EMF, there are certain checkpoints which you need to take into consideration. First is, how is the magnetic field and the aerial vector? Only when you decide these two, you will be able to decide what is the angle. Right? When you have these three parameters, what can you define? You can define the magnetic flux. So you always need to, if you see the whole problem based on Faraday's law of electromagnetic induction, we'll be solving only two things. One is we will try to understand what is the initial value of flux, what is the final value of flux, and how much is the change that has occurred in a particular time. In addition, what you will do is, if you know the number of terms, you are just going to multiply that. Is that clear? Right? So that's how it works. Now I need to take the initial magnetic field to be how much? Earth's magnetic field is found to be 3 into 10 power 5 Tesla. I hope there is no doubt in that. So what is the initial area? Pi into r square. So pi into 10 power minus 2, the whole square. How much is that? So 10 power minus 2 times pi meter square. Is that clear? Am I clear with these 2 points? Now I have another question. Here, what is changing? And one more point I wanted to mention here is whenever flux is changing, right? So listen to this carefully, okay? Whenever you talk about the change in flux, flux is a physical quantity which is dependent on 3 other physical quantities. What are they? Magnetic field, area of the coil, and the orientation at the angle. That's right. So when they change, right, when the flux has to change, they will not change more than one parameter at a time. In the sense, if you see the previous problem, right, if you see the previous problem, what has happened is, the orientation was the same. If you remember what I did yesterday, that square problem, northeast direction, everything, right? Magnetic field was reduced to 0. Right? You remember that, no? So what happened is area. So B A theta. B was kept constant. Area was kept constant. Sorry. Area was kept constant. Orientation was kept constant. But magnetic field was changed. But in this problem, what is happening is magnetic field is kept constant. Area is also kept constant, but the orientation is changed. Magnitude, not the direction. So it can see, if they want, they can change the direction also. That is their wish. But mostly they will not give it to you, because if that kind of a scenario occurs, you need to use a lot of complex mathematics. Like you need to go with calculus. So generally they will not go to that extent, but still you can solve it in real time. Okay, for your syllabus purpose, what I'm trying to say is, only out of these 3, only one will be changed, not even 2. You can take my word on this. For CBSE, they will not ask more than 1. Am I clear? So like this, if you look at this problem, what is changing? orientation means you read the question carefully. There was a coil which was placed like this, and the magnetic field was in this direction. Now, what is the direction of aerial vector? It's the same direction. So you can change it with respect to a two-dimensional surface. Aerial vector can be considered in any direction. We are free to choose them. So I will take, in this case, I will take DE and area to be in the same direction. Now, what is the coil? What is done to the coil? The coil is rotated through an angle of 180 degrees. By doing it, the aerial vector which was there like this got turned like this, whereas the magnetic field is still in the same direction. So what is the change in value of theta that has taken place? So from 0 degrees, it has changed to 180 degrees in how much time? In 0.25 seconds. During this time, there is a magnetic field, there is an EMF that is induced. Does that make sense? Right? So I already gave you the hint of how to take the data. Right? Yesterday itself, I told you how to take the data. So first, write down, put a line like this. Okay. Any problem, this is the only algorithm. You need not think of anything else outside this. Just search for this data, you will get the answer. For line initial, final. So what are the three parameters? B initial, B final. What is B initial? 3 into 10 power minus 5 Tesla. B final is 3 into 10 power minus 5 Tesla. What about area initial? 10 power minus 2 pi. What is area final? 10 power minus 2 pi. Both are in meters square. What is theta initial? If you take theta initial to be 0, then theta final will be 180 degrees. Here, they would have asked you only the magnitude because they didn't tell you what is the direction of B. Read the question carefully. Did they tell you B is in this particular direction? They were never spoken anywhere. They didn't tell any direction. There is a horizontal component of Earth's magnetic field existing. But we don't know whether it is existing along X direction, Y direction, or anything. Are you guys relaxed? Relaxed. No tension. Yeah. So that's what is happening. And how much is the time that we have taken? So we have taken 0.25 seconds. Is that right? Now can you try to apply the formula and tell me? So they have asked only the magnitude of induced EMF. So directly you can write it as N into delta phi by delta T. Guys, I hope you understood. I hope you understood when to use delta, when to use D. You know this, right? So throughout physics, same logic. Delta is used when the time is measurable quantity. T is used when it is instantaneous value. So here it is not instantaneous. I hope you understood because it takes 0.25 seconds. So can you guys do this? So N into what? For this problem it is. Because that will vary from place to place. No? That's what we learned in previous chapter. Can you calculate the value and tell me? So try to figure out the method. Well, pi into 10 power minus 4. Maybe value, right? 4. Yeah, I think that is the value. So N is 500. So one more thing, I think I already told this to you. When you read a question, right? You see the first word itself will tell you whether they are talking about 1 turn or n turns. So what is the keyword? If they use the word loop, it is 1 turn. Coil, it is n. Coil is always wound. Okay. So even if you leave it as 12 pi, no harm in it. 12 pi into 10 power minus 4, but don't forget the unit, Weber. Sorry, Weber, old. Because it is the EMF value. Panish Purida, are you able to understand? Those who are online, are you able to understand? Yes or no?
Yes, sir. Yes, sir.
Please make a note of this. So it is 12 pi into 10 power minus 4 Weber. So once you find the EMF, current is easy. Right? I is equal to E by R 1.9 into 10 power minus 3 ampere. That's it. I'm hoping it is clear. Right. So this is all about Faraday's law. Okay. As I told you in this whole chapter, you will be using only this logic. Nothing is there. So if you want to induce EMF, what are you supposed to do? Change the magnetic flux. That's it. So if somebody asks you, I want you to generate EMF and give it to me, you say, you give me a coil, I'll change the magnetic flux, I'll generate the EMF and give it to you. That's it. Okay. Now, there is another important point. Yesterday, when I gave you Faraday's law of electromagnetic induction, I told E is equal to minus N into d phi by dt. Right? So minus N triple another, it is the significance of Lenz's law. So we need to understand that. I want you to understand why Lenz's law is speaking like that. Okay. So there is a simulation that we saw yesterday. Right? Actually, you're able to see something small. It's becoming small. You saw the letters are small. But it is not from the subject. I wanted to explain something. So you know what is the name of this cable? You call it as HDMI cable. Full form even I don't know. Okay, when I connected this laptop, you're able to see very small. The letters are also very small. Actually, what should happen is whatever is projected in my laptop should exactly come there. Now, problem is when I connect it, no, in my laptop also all letters have become small. In this one, any idea why that is happening? That's right. But whatever is here, it should get magnified and projected there. Now, why is my laptop actually showing things small? I am sure you will not know, but I want to see if somebody knows it. Try to find out the answer and tell. This has something to. I'll give you the hint. Something called as aspect ratio. I'm not sure if you've heard of. Have you heard of this? Generally, TVs and normal laptops have aspect ratio of 16:9. 16:9, correct. This laptop's problem is it is 16:10. So that is why it is not getting adjusted. But next time when I'm writing, see how the sides will be empty. You think about that and tell. This tab it is different. Any idea what is the number? It's called 4:3. There is going on. If at all you want to become some designer of laptops or TVs, it will be helpful for you. You should know these problems. Right. Because end user like me will struggle like this. Right? Online people would have not even understood what I'm trying to speak. Forget it. Those who are there, forget it. Okay. We'll get back to the subject. So I was talking about Lenz's law, right? So what does Lenz's law state? That negative sign. That's all we know as of now. But why that negative sign? We'll observe it. For that, I want you all to concentrate on the motion of electrons. Okay, everybody, please pay attention. Again, a problem will occur. It is running on internet. When I move it, sudden up it. I don't know when it will go. So concentrate and see what is happening. Okay. So I have a magnet. I think I told you yesterday. I don't know whether I told you or the other batch. The strength of the magnetic field is changing. Did I tell you guys about it? Yeah. Strength of the magnetic field is changing. But when you're trying to move the north pole closer to the, when I'm trying to move the north pole closer to the coil, look at the way the electrons are going to move. Don't concentrate on the bulb. Bulb will glow. Okay. What happened? It started moving downward. Okay, anti-clockwise or clockwise and that depends on which side you're seeing it from. Okay. That's right, but it depends on which side. Are you seeing it from the side of the magnet or on the other side? Side of the magnet, it's anti-clockwise. Sir. It's a clockwise. Now, forget about clockwise, anti-clockwise. Let me make my point simple. Okay. When I'm moving it closer, are the electrons moving down or up when I see it from this side? I'm seeing it like this. Okay. I'm seeing whether the electrons are moving down or up when I move the magnet. Concentrate on that. Down, down, up. So that is when you have this north pole thing, right? Now I want to change something. So when you took the north pole closer, what happened? Now, when you took the north pole closer, the electrons went down. When you took the north pole away, the electrons went up. Now what happens when you take the south pole closer? What do you expect? It didn't move up. See. But you told up. You guessed it like that. Now. So one thing you observe, whether I move the north pole closer or south pole closer, one thing that I can observe is the electrons were moving down. So which side you need to observe, that I'll tell you. When I moved the north pole away or south pole away, the electrons started moving up. Is very clear? Okay. Now, I'll come back to this position. Now I want to get to the second step. So when I move so you told about clockwise and anti-clockwise, right? We'll come to that. When I move the north pole closer, the electrons move down. So when you see it from the side of the magnet, okay, when you see it from the side of the magnet, in which direction are the electrons moving? Clockwise. I hope everyone is clear. Those who are online, are you clear? Please give me a confirmation.
Yes, sir.
Right? So it moves in the clockwise direction. Right? So clockwise current should generate. Clockwise current should generate south pole. So can I say that is south pole? Can I say on the side of magnet, when you are moving the north pole, south pole is getting generated? My job is to confuse you. My job is to confuse you. That's the only hint I can give you. What are those dots? So which particles move in the clockwise direction? Electrons move in the clockwise direction. In which direction will the current be? Anti-clockwise. Right? So now you correct yourself and tell me. Concentrate. Okay. When I move the north pole closer, electrons move in the clockwise direction. Accepted? Then what is the direction of current? Anti-clockwise. Means what pole is getting generated? So the north pole, the anti-clockwise current or the clockwise thing is decided by the current, not by the motion of electrons. So first lesson to be learned. Okay. So electrons revolve in anti-clockwise direction. So it is north pole. Means north pole is going closer. You are able to see north pole. Right. When I move the north pole away, what direction were the electrons moving? Electrons are moving in anti-clockwise direction. So what is the direction of current? Clockwise. So it is south pole. So when north pole was going closer to the coil, the same pole got generated. Whereas when the north pole was moving away from the coil, opposite pole got generated. Same is the case whether you move a north pole or a south pole. If you want, you can test it now. Now you have all the points in your mind. Now I want you all to think and tell me. Check. Check. So when you move the south pole, electrons are moving down. So from the side of magnet, if you see current is flowing in the current is in the clockwise. So south pole. So when south pole is moved closer, south pole got generated. When north pole was moved closer, north pole got generated. Whereas when you move a particular pole away from the coil, what pole is getting generated? The opposite poles are getting generated. So it is exactly trying to do the reverse operation of what you are trying to do. That is why the significance of minus sign. I'll come to that point. Whichever magnet you use, anything you use, any magnet. Not sure that one. I never thought of chickens. So generally for these activities, right, we use only bar magnets or other coils. You can use a current carrying coil also. Right. So let me think of this. I'll think and get back on this. But coming back to this point, when you speak about Lenz's law, right, whatever you're trying to do, the coil will behave exactly the opposite way. Now let's forget about north pole and south pole. Tell me one thing, whichever pole I take it closer to the coil, am I trying to increase the flux or decrease the flux? If I try to increase the flux, what pole is getting generated? Means if I move a south pole, south pole. If I move a north pole, north pole. So south pole and south pole will do what? They will repel. Means the south pole, when you are moving, there is something that is getting created here, right? This creation is trying to repel. Means when you try to increase the flux, it is trying to decrease the flux. Is that right? Whereas when you move the south pole away, you are trying to decrease the flux. So what pole is getting generated? North pole. Means it is trying to attract. Are you able to understand what I'm trying to say, guys? So this is the tricky part. This is what I want you to understand. Why same poles are getting generated is because when you try to increase the flux, same poles will get generated so that they can oppose the magnet which is coming close to it. Similarly, if you try to take it away, the opposite poles will get generated so that it's trying to attract the magnet that you're trying to take it away. Means whatever you're trying to create, right, it is exactly opposing. And that is what is exactly Lenz's law all about. So having all these things in mind, let's write down the statement for Lenz's law. Please write it. So it states that so I've written, you know the spelling of Lenz's law, right? L-E-N-Z. Okay, L-E-N-Z. The law states, it states that the EMF will get induced. It states that the EMF will get induced in such a way. It states that the EMF will get induced in such a way that it will always, the EMF will get induced in such a way that, it will always try to oppose the cause. It will always try to oppose the cause.
Sir, what is after oppose? After oppose, sir.
It will always oppose the cause which is trying to produce it. It will always try to oppose the cause, C-A-U-S-E, which is trying to produce it. You want me to repeat the whole statement? Want me to repeat it? It states that the EMF is induced in such a direction. After that, what did I say? In such a direction that comma, it will always oppose the cause which is producing it. Okay. So write down a note at the bottom. Write a note. Whenever we are trying to increase the flux, same pole will get generated. Whenever we are trying to increase the flux, same pole will get generated. And when we are trying to decrease the flux, opposite pole gets generated. Is it clear? Whenever we try to increase the flux, same pole gets generated. And whenever we try to decrease the flux, opposite pole gets generated. Okay. So with this knowledge, are we ready to solve problems based on Lenz's law? Now I hope it makes more sense of why there is a minus sign in Faraday's law. So initially, maybe when we found it out, you would have not mentioned the minus. Later, these kind of observations came and that minus was added at later point, right? So based on this, we will work on some problems. Okay, so concentrate. First, I'll give you the hints, I teach you. Then the remaining problems you try. Okay, so if you're able to solve this part, half of the chapter is in your hand. Listen. So figure 6.7 shows planar loops of different shapes moving out of or into a region of magnetic field, which is directed normal to the plane of the loop, away from the reader. Move that point away from the reader. Determine the direction of induced current in each loop using Lenz's law. So the Lenz's law statement is there, right? There you go and strike off induced EMF and you can change it as induced current. That makes more sense. In Lenz's law, I told the EMF will get induced. No. Wherever EMF is there, strike it off and change it to current. In Lenz's law statement, it states that EMF is induced. No, did I say EMF cut to write it as current? Okay. Now, shall we proceed with this problem? So let's not break our heads. It's very simple. Okay, there is a small technique that we need to follow. One, they told that the magnetic field is away from the reader. Okay, if there is an into mark. Okay. So whenever you solve a problem based on Lenz's law, especially when you're facing a paper, first thing is you should understand you are acting as which pole. So you are acting as which pole is what we need to find first. So if you observe, paper is receiving the magnetic field lengths. So which pole has a tendency to receive field lengths? South. So your paper is acting like south pole. If that is the case, who are you? We are a north pole. So north pole, and there is a coil which is moving in front of us. See, as a reader, what are you doing? You're seeing this, no? As a reader, you're the one which is facing. Means this coil ABCD in the anti-clockwise direction is actually facing you. It is facing the north pole. Now you see. So this point is clear. First step is you find out which pole you are. Second step is try to find out whether the coil's motion is increasing the flux or decreasing the flux. In the first case, it is entering into the magnetic field, means it is able to take more number of field lengths. Hence the flux is increasing. So I gave you a statement under note. When flux is increasing, same pole gets generated, but same pole as whom? Same pole as you. So who are you? North pole. So what pole will you be able? You will be able to see this as north pole. Means the current will start flowing in the anti-clockwise direction. So the answer is B, C, D, A, B. Is it clear? Sure. So first point is clear. Your north pole, you are convinced. Okay. You understood that flux is increasing. Convinced with that? Because it is entering into the field, flux is increasing. So when flux is increasing, what pole will get generated? The same pole as whatever you are. If the flux is increasing, the same pole as whatever you are will get generated. Means it will generate a north pole. North pole means what is the direction of current? Anti-clockwise. That is why I took the loop as BCDAB. Is it clear or not? Yes. So using the same logic, but before that, those who are online, I hope you understood, right?
Sir, can you repeat how is flux increasing?
Because the coil is moving into the magnetic flux, magnetic region. See, when the coil is here, what are the number of field lines through it? I will draw a diagram. Nitish, answer this. When the coil is outside, what are the number of field lines through it?
Sir, nothing.
Nothing. So when it starts entering into this, are the number of field lines through it increasing or decreasing?
It increases.
So number of field lines is nothing but flux only, no?
Yes, sir.
So that is why I told it is increasing.
Okay, okay, sir.
Yeah. So what about the second case, guys? Clockwise, because the coil is moving out of the plane. Out of the plane means its flux is decreasing. Decreasing now opposite pole of what you are. So your north pole, so opposite pole will be south pole. So the current should flow in the clockwise direction, AC, BA. What about the third one? So coil is moving outside, again, south pole will get generated. So south pole means the current will be in the direction of A, B, C, D, A. Is it right? That's it. So please copy this. Please copy this. If there is any doubt, get it clarified. Shall I proceed? Which arrow? That is the direction of motion. This is the direction of motion. Right? Shall we proceed to the next one? This one. So let's see 6.5. So I want you all to think calmly and then answer. Don't be in a hurry to answer. First, read the question. So there is a closed loop which is held stationary. So closed loop, first thing, it has a tendency to generate EMF. So how is it held? Stationary. In the magnetic field between the north and south poles of two permanent magnets held fixed. So north pole and south pole of two permanent magnets are held fixed. In between, you have a coil which is also stationary. Okay. Can we hope to generate current in the loop by using very strong magnets? You read the question. Answer is no. Okay. Because if you see in the question, there are three keywords: stationary and magnets are also addressed. So when there is no relative motion, what does Faraday's law state? There is no EMF induced. However strong magnet you are going to use, unless there is a relative motion existing between them, because they didn't ask, can I generate high value of current by using a strong magnet? No. How will you do it? To increase it, you need to do something with the magnet. You have to put it in motion. Or else what you need to do is you need to have a current carrying coil to which you keep connecting the sources where current is increasing always. That's a tedious process. That doesn't happen in real time. Okay. I hope everyone understood the answer for A. It is no. What is the reason for it? Because every part of the system is stationary. Since there is no relative motion, that is a keyword they expect in exam. Since there is no relative motion existing between the coil and the magnets, no EMF is induced. Second, a closed loop moves normal to the constant electric field. There is a closed loop which is moving normal, which is moving perpendicular to a constant electric field, which is existing between plates of a large capacitor. Okay, is a current induced in the loop? Is a current induced in the loop first when it is completely placed inside the region between the plates of the capacitor. Second, when it is partially inside and partially outside. Remember, the electric field is always normal to the plane of the loop. Will you be able to generate current in it? If you read the question carefully, you will get it. We can't or we can. Why? Is that the reason? What does Faraday's law state again? EMF is induced only when there is a change in magnetic flux. What do we have to do with electric field? Nothing. Even if there is a case where you are increasing or decreasing the electric field, you can never induce it because EMF is always induced with a change in magnetic flux. It is not happening with the change in electric flux. Nothing. Electric flux has nothing to do. Which one? There is a reason why those charged particles are actually getting into motion. It is because of the force they are experiencing. You know Lorentz force. F is equal to Q into V vector cross V vector. It is because of that reason they are able to experience that force and be in a motion when you create the change. So the answer to part B is no, because change in electric flux can never induce EMF. So I hope this part is also clear. What about C? So see, these four questions are tricky only. Concentrate and read. There is a rectangular loop and a circular loop. Okay, there is a rectangular loop and a circular loop, which are moving out of uniform magnetic field to a field-free region with a constant velocity. So initially, where were those two coils present or loops present? In the magnetic field and the uniform magnetic field. Now they started moving out of the uniform magnetic field into the field-free region. By doing so, in which loop do you expect the induced EMF to be a constant? So one thing they are confirming is in both the cases EMF is induced. Why? Because there is a change in flux. There is a loss of area that is happening. Right? So in both the cases, if you see comparatively, which one is the case where the induced EMF is a constant? Observe it. For my induced EMF to be a constant means after 1 second, if I am calculating the value to be 1 volt, after 2 seconds also it should be 1 volt only. That is the meaning of being constant. In which case will it be constant? The answer is in the case of rectangle, because they gave you one more hint that it is moving with a constant velocity, right? So when you take a rectangle, right, let's say after 1 second, this is the amount of area that has come out. In the next 1 second, the same amount of area would have come out. So what is constant? Magnetic field is constant, orientation is constant. The amount of area that is coming out is also a constant in the case of a rectangle. Whereas in the case of a circle, what happens is some portion would have come out the second case, more portion would have come out, and the third case, the whole circle would have come out. So if you see, the curvature will have different lengths. Whereas when you talk about a rectangle, a specific area is what is coming out because of the constant velocity. Now from this, what you can understand is the induced EMF is going to be a constant in the case of a rectangular loop. So because it is a rate of change of area, that is a more technical term. But if you have to visualize, the amount of area that is coming out per unit time is always different for a circle because of the curvature. Whereas for a rectangle, it is constant. If one square is coming out, next square will come out in the next second. So the change in flux is always a constant. So EMF is also a constant. So the keyword that they are expecting, that they will expect in the exam is rate of change of area of the loop in the case of circle is different, whereas in the case of rectangle it is a fixed value. Area dA by dt. dA by dt you can also call it as aerial speed. Aerial speed. Last year gravitational potential. Like this. Okay. Rhombus also it is different. Different because small triangle will come out, then bigger triangle will come out. But the shape is not a constant. Is it the same shape that is coming out? That is the reason. So shape is same, but the size of the shape is varying. Once you will get a small triangle, then big, it keeps going. Whereas in the case of rectangle, if you get a rectangular piece outside, the same rectangular piece will come out again. It will go something like that. Right. So fourth one, I want you to think. Predict the polarity of capacitor in the situation described in figure 6.9. So in both, one hint I want to tell you. So guys, I want you to concentrate. Whenever you have these kind of loops, right, you will be able to see the center of that loop only on one side. So generally, see, if the coil is like this, see, if this is a circle, okay, had it been a circle, when you see it in a plane, it will look like a perfect structure, circle. Whereas when you see perpendicular to the plane, how will it appear? It will appear like a straight line. Whereas when you slightly tilt it like this, it will appear like an ellipse. So that's what is given there. So though it looks like an ellipse, it's not an ellipse, it's a circle, which is projected into a three-dimensional kind of structure. Right. Secondly, when you take the circle, the center is here and here. So center is at this point. Is it right? So when you see, the coil is tilted either in this direction or in this direction. So how you find it? Which direction it is tilted? It is very simple. In this case, if you see, you are able to see the center on the right hand side or left hand side. You are able to see it on the right hand side. Means keep your hand straight, and wherever you are able to see the center, turn that part towards your face. So it is actually this palm that you are able to see. Breathe, Dada. So this is a straight line. So when you turn it like this, you are able to see the palm. For example, where you are able to see the circle on this side, the center on this side, then you turn it like this, you will be able to see your knuckles. So this is how it works. In this case, I am able to see my palm where I have a capacitor. Now observe, in both the cases, what is happening? Either of the poles are moved towards the coil. So in the first case, you are moving the north pole towards the coil. So what pole will get generated this side? North pole. And what pole will get generated this side? South pole. Right? When it is going to be south pole, what is the direction of current? Your hand is like this. The current starts flowing in the clockwise direction, your palm. So clockwise direction in the palm, which end should be positive and which one should be negative? How A is positive? Actually, there is a mistake. It is B to E. Because where is A according to you? It's a capacitor. Where is A according to you? See, if you take your hand, is that AB away from your hand or is it closer to your eyes? Really, not necessarily. That's not. Look at the diagram. Where top and bottom? Incomplete circle. So they have inserted a capacitor. No. Where did they put the capacitor? Is it away from you or is it on this side? So when you see it like this, right? Is the capacitor put here or this side? How are you able to? You are able to see it this side. I am able to see. I am able to see it on the other side. Actual diagram here. Okay. That's what I'm asking. See, I'm able to see it in two perspectives. I don't know how to explain it. Listen. See, when you turn your hand like this, there is one portion which is closer to your face. There is one portion which is away from your face. You put the capacitor here. This is the center with respect. So I'm able to see my palm. So this is the coil. I'm able to see my palm. This is a capacitor according to you here or here. You're saying here, no. When it is here, then the current flows in the clockwise direction. Is that what you're saying? So when the current flows in clockwise direction, which side should be positive? How will A be positive? B will be positive because current flows from higher to lower potential. This is what I wanted to explain. Current flows from higher to lower potential outside the battery. Whereas it flows from negative to positive inside the battery. Capacitor, it is acting like a battery only. It is an energy source as of now, right? So which one should get the positive value? So I'm not, this question is ambiguous. They have given it as A only. But if I'm not wrong, they would have given it A because the capacitor is taken here. If it is taken here, then the current flows in clockwise direction. So A is given. No need. No need. But what I am able to observe is it is away only. This question has always been a problem. So according to me, answer is B is positive and A is negative. Because if it is like this, no, you keep the capacitor at the other end. You are convinced with that factor. It is away from you. That's what you are also able to see. None of you are able to see it closer. So when it is away, the current, when it has to flow in the clockwise direction, who should be the energy source? Whether B will be the energy source, B will be the starting point, or A will be the starting point. Current flows from higher to lower potential outside. So current should flow from higher to lower. So when you take a battery, right? What is the direction of current you take? You take it like this. So what does that mean? Current flows from higher potential to lower potential outside the battery, whereas from negative to positive inside the battery. Only then it can complete a loop. Right? Same logic is applicable. So actually the answer should have been B is positive and A is negative. They have made a mistake. This diagram could have been more clear. They didn't give a clear perspective of where the capacitor is. So generally, if something is away from you, they should use dotted lines in three-dimensional structure. But it's okay. B is positive, A is negative. Okay, please make a note of that. Is that point clear? So those who are online, I hope you're following it, right?
Yes, sir.
Yes, sir.
Okay. Right, this is a very important question. So after that, you have some problems with the exercise. We can solve 2 problems for today. Remaining we'll do it in the next class. So try to solve the first one. Okay. Concentrate. Check which side you are able to see. How is the coil placed? Are you able to see? I'll only focus on left hand. Okay, I'm not taking right hand. If you take your left hand, are you able to see the palm or knuckle? So first case, you are able to see the palm. So towards the palm, 11th, yeah. Harini, huh? Okay. So when you move the south pole closer, right? When you move the south pole closer, what pole will your palm rep? Your palm behaves like a south pole. So the current flows in the clockwise direction on your palm, right? So current is in clockwise direction means it goes like this and there is a jump. This is what I told you. Constant. Look at the loop. This you can't see it in the book. Or jump theory, right? So it jumps and goes to Q first. So it jumps to Q first. Then it goes to R, then P, then Q. So Q, R, P, Q is the answer. I hope you are able to understand, right? It is a little bit because of zooming. But P kept the dotted line is connected to P. Yes. So first, see this kind of confusion will occur. If a clockwise now, this is the first loop. In the red color line is the first loop. On the first loop, current is clockwise now. Where is it entering? Jump on it, it is going to Q only. No? So that is why it starts with Q, goes to R, P, and then again comes to Q. So if you write QRP, it is wrong. You should write always QRPQ. It is then you are completing the loop. Is that clear?
So if the north side of the bracket is then it's not P.
Yes.
PR.
PRQ. That is, had it been a north pole. So using the same logic, I want you guys to solve problem B. That is your headache, right? However you want, tell me that. If you want, I'll zoom and show you whichever place you want. It's PRQP. What is the MPRQP? So when you're moving the south pole, this also acts like south pole. So current flows in the clockwise direction. So in the first loop, is the current going to Q or to the subsequent loop, the next loop, right? When it goes to the next loop, any doubt? So when it goes to the subsequent loop, first it will go to the other part. So it starts at P and the answer will be PR QP for this loop. Then what about this one? So how I will do it, listen to this carefully. When north is moving away, this will be south pole. Accepted? When north is moving away, this side is south pole. I always look from the other end. I'm always comfortable from the side that I'm able to see. So if this is south pole, I will take this as north pole. Because it's a magnet, correct? So when it is north pole, then the current will be in the anti-clockwise direction. So where is it entering? Yes. Is that what you guys told? Okay. Why is that? Is it clear? So this is how you need to solve problems based on Lenz's law. The other problems are a little tricky, which we'll solve it in the next session. Okay. So we have test also. No. So that's it from my side for today with respect to physics. Any doubt? I hope it's clear, right? So these two are the important. After that, the chapter is very simple. We can complete it faster. Don't worry about it. Okay. So, yeah. You can take just a 5 minutes break, then you can start writing the test. Guys, those who are online, are you clear?
Yes, sir.
Yes, sir.
Okay. Yeah, we'll wind up, guys. Thank you.
Thank you, sir.